In the fast-paced world of computer science, efficiency and performance are of paramount importance. The ability to design and analyze algorithms with speed and scalability can make all the difference in developing high-quality software solutions. That's where complexity analysis and big O notation come into play. Understanding the intricacies of algorithmic complexity and its application in problem solving is a crucial skill for any computer scientist, programmer, or enthusiast. Welcome to Mastering Complexity, a comprehensive guide to big O complexity in DSA problem solving. This book serves as your roadmap to unravel the mysteries of complexity analysis and empower you to optimize your code and tackle algorithmic challenges with confidence. We begin our journey by exploring the history and evolution of complexity in computer science. From the early days of algorithmic analysis to the modern complexities faced in solving real-world problems, we lay the foundation for understanding the significance of complexity analysis in today's computing landscape. Next, we delve into the core concepts of complexity, introducing you to big O notation and its role in quantifying the performance of algorithms. We demystify the language of complexity and equip you with the tools to analyze and compare the efficiency of different algorithms to make these concepts more tangible. We draw on real-world analogies that illustrate the principles of complexity in relatable terms. Building upon this knowledge, we explore the best, worst, and expected case scenarios in complexity analysis. You will learn how to evaluate the performance of algorithms under different input conditions and gain insights into the factors that influence algorithmic efficiency. With a solid understanding of complexity analysis in place, we shift our focus to popular data structures and algorithms, DSA. We dissect these essential building blocks of computer science, providing detailed code examples and explanations of their big O complexities. By studying the inner workings and analyzing the performance characteristics of these algorithms, you will gain valuable insights into designing efficient solutions to a wide range of problems. But complexity analysis is not just about theory. It is a practical skill that requires hands-on practice. That's why we have curated a collection of 15 famous DSA problems for you to solve. Each problem is accompanied by detailed code implementations and an in-depth analysis of its big O complexity. By actively engaging with these problems, you will sharpen your problem-solving skills, enhance your algorithmic thinking, and develop a keen eye for optimizing code performance. Throughout the book, we also explore advanced topics and considerations in complexity analysis. We discuss techniques for dropping constants and non-dominant terms, explore the implications of add and multiply runtimes, dive into the concept of amortized time, and understand the intricacies of logarithmic and recursive runtimes. Whether you are a student, a professional developer, or an algorithm enthusiast, Mastering Complexity aims to be your comprehensive guide to understanding and applying big O complexity analysis. We invite you to embark on this enlightening journey, where you will unravel the mysteries of complexity, gain the skills to create efficient algorithms, and unlock the potential to solve complex problems with elegance and precision. Let us embark on this exciting adventure together and master the art of complexity analysis. DSA Shorts. Welcome to Mastering Complexity, a comprehensive guide to big O complexity in DSA problem solving. In the ever-evolving field of computer science, understanding the efficiency and performance of algorithms is paramount. Whether you are a student embarking on a journey in computer science, a professional seeking to optimize code, or an enthusiast passionate about algorithmic problem solving, This book is designed to be your trusted companion. Complexity analysis lies at the heart of algorithmic efficiency, and mastering it is crucial for developing robust and scalable software solutions. This book aims to demystify the world of complexity by providing a comprehensive guide to Big O notation and its application in analyzing algorithmic performance. We will explore the origins and evolution of complexity in computer science, tracing its historical context and relevance in modern-day problem solving. Throughout the pages of this book, we will dive into the fundamental concepts of complexity, laying a solid foundation for understanding the intricacies of Big O notation. We will explore best, worst, and expected case scenarios, equipping you with the tools to evaluate the performance of algorithms under different circumstances. Real-world analogies will be employed to make complex ideas more approachable and relatable, ensuring a smooth learning experience. Beyond theory, this book takes a practical approach to complexity analysis. We will dissect popular data structures in algorithms, DSA, and examine their Big O complexities in detail. By providing code examples and explanations, you will gain a deep understanding of the efficiency and performance characteristics of these essential algorithms through hands-on practice. You will sharpen your problem-solving skills and be better equipped to tackle algorithmic challenges. In addition to exploring the complexities of well-known algorithms, we have curated a collection of 15 famous DSA problems with detailed code implementations. Each problem serves as an opportunity for you to apply your knowledge and analyze its Big O complexity. By tackling these problems, you will gain confidence in evaluating and optimizing the performance of your own algorithms. Throughout this journey, remember that complexity analysis is not a one-size-fits-all approach. We will delve into considerations such as dropping constants, non-dominant terms, add and multiply runtimes, amortized time, log n, recursive runtime, and more. By understanding these nuances, you will be able to navigate the intricacies of complexity analysis with confidence and precision. Whether you are reading this book cover to cover or using it as a reference guide, our goal is to empower you with the knowledge and skills to master Big O complexity and excel in algorithmic problem solving. We invite you to embark on this exciting journey, explore the depths of complexity, and unlock the secrets to creating efficient and optimized algorithms. Happy reading and happy problem solving. DSA Shorts. The history of complexity in computer science is intertwined with the evolution of algorithms and the quest for understanding the efficiency and performance of computational processes. As computer scientists sought to solve complex problems and optimize resource utilization, the concept of complexity emerged as a fundamental measure of algorithmic efficiency. The study of complexity theory aims to analyze and classify the inherent difficulty of problems, the resources required to solve them, and the limitations of computation itself. Over the years, researchers have developed various notations, techniques, and frameworks to describe and compare the complexity of algorithms, leading to a deeper understanding of computation's inherent constraints and possibilities. This journey through the history of complexity in computer science has paved the way for the development of efficient algorithms, the identification of intractable problems, and the exploration of the boundaries of what can and cannot be computed efficiently. The concept of algorithmic complexity and the notation used to express it, including Big O notation, have evolved over time as computer science has developed as a field. Let's explore the history of complexity in computer science in detail. Early concepts of complexity. The study of algorithmic complexity traces its roots back to the early days of computer science. In the 1960s, researchers recognized the need to analyze and compare algorithms based on their efficiency and resource requirements. Donald Knuth's influential book, The Art of Computer Programming, published in the late 1960s and early 1970s, provided a comprehensive analysis of various algorithms. Knuth introduced the notion of order of magnitude to describe the growth rate of functions and algorithms, though he did not use formal notation like Big O at that time. Landau's symbol and Bachmann-Landau notation. In the early 20th century, the German mathematician Edmund Landau introduced the concept of order of magnitude, or Landau's symbol, in number theory. He used symbols like O, omega, and theta to express the behavior of functions. Later, in the 19th and early 20th centuries, the German mathematician Paul Bachmann and the German astronomer and mathematician Johann August W. Hagedorn independently developed similar notation to analyze the growth of functions. However, these notations did not gain widespread adoption in computer science. Big O notation. The formalization and popularization of Big O notation as the standard method for expressing algorithmic complexity is credited to computer scientists who emerged in the 1960s and 1970s. In 1962, the Russian mathematician A. Markov used Big O notation to describe the probability distribution of the number of steps required by certain algorithms. However, his work did not initially receive widespread attention. In 1971, American computer scientist Jack Schwartz introduced Big O notation in his book, Data Structures and Their Algorithms. Schwartz's book helped establish Big O notation as a common language for discussing algorithmic complexity. Around the same time, in 1972, American computer scientist Donald Knuth also adopted Big O notation in the second volume of The Art of Computer Programming. Knuth's influence and his emphasis on algorithmic efficiency contributed significantly to the widespread acceptance and usage of Big O notation. Big O notation provides a standardized way to describe the upper bound or worst-case behavior of an algorithm's time or space requirements. It allows researchers, engineers, and programmers to compare algorithms, make informed design choices, and analyze the scalability of solutions. Further developments. Since the establishment of Big O notation, complexity theory has become a prominent and active field of research in computer science. It has expanded beyond worst-case analysis to include average-case and best-case analysis, amortized analysis, and more nuanced measures of complexity. Complexity classes, such as P, polynomial time, and NP, non-deterministic polynomial time, have been defined to categorize problems based on their solvability and computational complexity. The study of complexity classes has led to fundamental questions about the relationships between problems and the existence of efficient algorithms for solving them. Complexity theory has also been extended to include space complexity, communication complexity, and other resource-based analyses, reflecting the growing importance of various resources in algorithm design and analysis. Today, the understanding of algorithmic complexity and the use of Big O notation are essential components of computer science education and research. They provide a framework for analyzing and comparing algorithms, optimizing performance, and understanding the limits of computational feasibility. In computer science, complexity refers to the analysis and measurement of the resources required by an algorithm or a computational problem. It helps in understanding how the performance of an algorithm or the efficiency of a solution changes with the input size. Complexity analysis provides a quantitative measure of the time and space requirements of algorithms and helps in comparing and selecting the most suitable algorithm or data structure for a given problem. In the context of data structures and algorithms, DSA, complexity analysis is particularly important. It allows us to evaluate the efficiency and scalability of different algorithms, helping us choose the best approach to solve a problem. Complexity analysis focuses on two main aspects. Time complexity. Time complexity measures the amount of time or the number of operations required by an algorithm to solve a problem as a function of the input size. It provides an estimation of how the runtime of an algorithm grows with larger inputs. Time complexity is usually expressed using big O notation, which represents the upper bound on the growth rate of the algorithm's time requirements. It describes the worst-case scenario, providing an asymptotic upper limit on the algorithm's performance. Analyzing time complexity helps answer questions like, how does the algorithm's runtime change as the input size increases? Does the algorithm run in constant time, logarithmic time, linear time, or worse? By understanding the time complexity of an algorithm, we can make informed decisions about algorithm selection and determine whether an algorithm will be efficient enough to handle large input sizes. Space complexity. Space complexity measures the amount of memory or additional space required by an algorithm to solve a problem as a function of the input size. It quantifies how the memory usage of an algorithm scales with larger inputs. Space complexity is also expressed using big O notation, which provides an upper bound on the growth rate of the algorithm's space requirements. It describes the worst-case scenario in terms of memory usage. Analyzing space complexity helps answer questions like, how much additional memory does the algorithm require as the input size increases? Does the algorithm use a constant amount of memory, linear space, or more? Understanding the space complexity is important, especially in situations where memory resources are limited or when dealing with large-scale data sets. By considering both time and space complexity, we can evaluate the efficiency and performance of algorithms and data structures. Complexity analysis allows us to compare different algorithms and choose the one that is most appropriate for a given problem, based on the available resources and the expected input size. Overall, complexity analysis plays a crucial role in computer science and DSA, helping us design efficient algorithms, optimize performance, and predict the behavior of algorithms and data structures under different scenarios. Big O notation is used in computer science to describe the performance or complexity of an algorithm. It provides an upper bound on the growth rate of the algorithm's time or space requirements as the input size increases. The notation is written as O, F, N, where F, N, represents a function that characterizes the algorithm's behavior. In simple terms, Big O notation tells us how the runtime of an algorithm or the amount of memory it requires grows relative to the size of the input. It helps us analyze and compare the efficiency of different algorithms, allowing us to choose the most suitable one for a given problem. Let's dive deeper into Big O notation and algorithmic complexity. Time complexity. Time complexity measures how the runtime of an algorithm grows as the input size increases. It answers the question, how many operations does the algorithm need to perform? Time complexity is typically expressed using Big O notation. Here are some common time complexity classes, ordered from best to worst performance. O. 1. Or constant time. The algorithm takes a constant amount of time, regardless of the input size. For example, accessing an element in an array by its index. O. Log n, or logarithmic time. The algorithm's runtime grows logarithmically with the input size. Common examples are binary search algorithms or certain divide and conquer algorithms. O. N, or linear time. The algorithm's runtime grows linearly with the input size. For example, iterating through each element in an array. O. N log n, or linearithmic time. The algorithm's runtime grows in proportion to n multiplied by the logarithm of n. Examples include efficient sorting algorithms like merge sort and quicksort. O. N squared, or quadratic time. The algorithm's runtime grows with the square of the input size. Nested loops iterating over the same input result in quadratic time complexity. O. N caret k, or polynomial time. The algorithm's runtime grows with the input size raised to a constant power k. Higher values of k indicate worse performance. O. 2 caret n, or exponential time. The algorithm's runtime grows exponentially with the input size. Recursive algorithms that solve problems by dividing them into smaller subproblems often have exponential time complexity. O. N, or factorial time. The algorithm's runtime grows with the factorial of the input size. This is the worst-case scenario, where the number of operations grows extremely quickly as the input size increases. Space complexity. Space complexity measures the amount of memory or additional space required by an algorithm to solve a problem. It also uses big O notation to describe how the space usage grows as the input size increases. Similar to time complexity, space complexity has different classes, such as O1, or constant space. The algorithm uses a fixed amount of memory that does not depend on the input size. O(n), or linear space. The amount of memory used by the algorithm grows linearly with the input size. O(n)k, or polynomial space. The amount of memory used grows with the input size raised to a constant power k. O(2)n), or exponential space. The algorithm's memory usage grows exponentially with the input size. It's worth noting that space complexity is not always as critical as time complexity, especially when dealing with modern computers that have ample memory. However, for certain applications or limited environments, minimizing space complexity becomes important. Understanding the time and space complexity of algorithms is crucial for designing efficient solutions, optimizing performance, and predicting how they will scale with larger inputs. It allows developers and researchers to make informed decisions when choosing algorithms or improving existing ones. Real-world analogies can help to understand the concept of big O complexity by relating it to everyday scenarios. Here are a few analogies to explain big O complexity. Waiting in line at a coffee shop. Imagine you are waiting in line at a coffee shop, and there are different people ahead of you. The time complexity can be compared to the number of people in front of you. If the coffee shop has a single line and serves customers in a first-come, first-served manner, O(n) complexity, the time it takes for you to get your coffee will increase linearly with the number of people in front of you. If there are 10 people ahead, it may take longer than when there are only 2 people ahead. However, if the coffee shop introduces a more efficient system like multiple parallel lines or an express lane, O(1) complexity, regardless of the number of people ahead, you will be served quickly. Searching for a book in a library. Imagine you are searching for a specific book in a library, and the books are arranged in a certain order. The time complexity can be compared to the number of books you need to search through. If the books are arranged randomly, You would need to check each book one by one. O-N. Complexity. Until you find the desired one. However, if the books are arranged in a well-organized and indexed manner. O-log n. Complexity. Such as using the Dewey Decimal System. You can perform a binary search, quickly narrowing down the search space and finding the book efficiently. Sorting a deck of cards. Consider the task of sorting a deck of cards. The time complexity can be compared to the number of comparisons and swaps required to sort the cards. If you use a simple algorithm like bubble sort, O-n squared, complexity, you would need to compare each card with every other card and perform swaps accordingly. As the number of cards increases, the time required to sort the deck would increase quadratically. However, if you use a more efficient algorithm like merge sort or quick sort, O-n log n, complexity, you can divide the deck into smaller subgroups, sort them individually, and then merge or partition them in a faster and more organized manner. Planning a dinner party. Imagine you are hosting a dinner party and need to plan the event. The time complexity can be compared to the number of guests you invite. If you decide to individually call and confirm attendance with each guest, O-n complexity, the time it takes to finalize the guest list will increase linearly with the number of guests. However, if you create an online RSVP form and guests can respond with a single click, O-1 complexity, the time required to collect and confirm responses remains constant, regardless of the number of guests. Shopping for groceries. Consider the task of shopping for groceries in a supermarket. The time complexity can be compared to the number of items on your shopping list if you search for each item by systematically going through every aisle. O-n complexity. The time it takes to complete the shopping will increase linearly with the number of items. However, if you organize your list based on the supermarket layout or use a shopping app that provides item locations, O-1 complexity, you can quickly locate and collect the items without scanning through the entire store. Traveling to a destination. Imagine you are planning a trip to a specific destination. The time complexity can be compared to the distance or number of miles you need to travel. If you take a route that requires you to stop at each town along the way, O-n complexity, the time it takes to reach your destination will increase linearly with the number of towns. However, if you choose a direct highway or a faster transportation method like a flight, O-1 complexity, the travel time remains constant, regardless of the number of stops or towns in between. These analogies help to illustrate how the complexity of algorithms relates to real-world scenarios, making it easier to understand the impact of different complexities on the efficiency of solving problems. When analyzing the time complexity of an algorithm using big O notation, it is important to consider different scenarios that can affect its performance. These scenarios are commonly referred to as the best case, worst case, and expected case. Let's delve into each of these cases in detail. Best case. The best case time complexity represents the scenario in which an algorithm performs optimally or has the lowest possible time requirement for a given input size. In other words, it describes the scenario that results in the best possible outcome in terms of time efficiency. The best case often occurs when the algorithm encounters favorable conditions, such as finding the target element early in a search or having an already sorted array for a sorting algorithm. However, the best case scenario is not always the most common or practical situation. In terms of big O notation, the best case complexity is denoted as omega. Omega It provides a lower bound on the growth rate of the algorithm's time complexity. Worst case. The worst case time complexity represents the scenario in which an algorithm performs the least efficiently or requires the maximum amount of time for a given input size. It describes the scenario that results in the worst possible outcome in terms of time efficiency. The worst case occurs when the algorithm encounters the least favorable conditions, such as the target element being at the end of a search or an array being sorted in reverse order. For a sorting algorithm, it helps establish an upper bound on the algorithm's time requirement, indicating the maximum time it can take regardless of the input. In terms of big O notation, the worst case complexity is denoted as O. Big O. It provides an upper bound on the growth rate of the algorithm's time complexity. Expected case. The expected case time complexity represents the average or typical scenario an algorithm encounters when processing various inputs. It takes into account the likelihood of different inputs occurring and computes the average time requirement based on their probabilities. The expected case depends on factors like the distribution of input data, the frequency of different input types, and the algorithm's design. It provides a more realistic estimate of an algorithm's performance than just considering the best or worst case. The expected case complexity is notated using theta notation. It represents both the lower and upper bounds of the algorithm's time complexity, indicating that the algorithm's performance is tightly bound within a certain range. It's important to note that best case, worst case, and expected case complexities are not mutually exclusive. An algorithm can have different time complexities under different scenarios. When discussing big O notation, the focus is usually on the worst case complexity as it provides an upper bound on the algorithm's performance. However, it's valuable to consider all three cases to have a comprehensive understanding of an algorithm's behavior and make informed decisions based on different scenarios. Example. Let's consider the example of a searching algorithm, specifically the binary search algorithm, to illustrate the best case, worst case, and expected case complexities. Binary search is an efficient search algorithm that works on a sorted array by repeatedly dividing the search space in half. Here's how it works. Best case scenario. The best case scenario for binary search occurs when the target element is exactly in the middle of the sorted array. In this case, the algorithm can find the element in just one comparison and immediately return the index. Best case time complexity. O(1). Constant time complexity. Explanation. The algorithm finds the target element in the first and only comparison, resulting in the best possible outcome. Worst case scenario. The worst case scenario for binary search occurs when the target element is either at the beginning or end of the array, or it does not exist in the array at all. In this case, the algorithm needs to repeatedly divide the search space until it either finds the target element or determines its absence. Worst case time complexity. O. Log n. Logarithmic time complexity. Explanation. With each comparison, binary search eliminates half of the remaining search space, resulting in a logarithmic growth rate. The algorithm requires a maximum of log n comparisons to find the element or determine its absence. Expected case scenario. The expected case scenario for binary search assumes that the target element is uniformly distributed across the sorted array. In this case, the algorithm has an equal chance of finding the element at any position within the array. Expected case time complexity. O. Log n. Logarithmic time complexity. Explanation. Since the target element is uniformly distributed, on average, Binary search eliminates half of the remaining search space with each comparison, leading to a logarithmic growth rate. The algorithm requires an average of log n comparisons to find the element or determine its absence. In summary, the best-case scenario for binary search occurs when the target element is in the middle, resulting in constant time complexity. The worst-case scenario arises when the target element is at the extremes or is absent, leading to logarithmic time complexity. The expected case scenario assumes a uniformly distributed target element, resulting in the same logarithmic time complexity as the worst case. These cases demonstrate the varying performance of the binary search algorithm under different scenarios. Data structures and algorithms, DSA, form the backbone of computer science, enabling efficient problem solving and algorithmic reasoning. When studying DSA, one essential aspect is understanding the performance characteristics of different data structures and algorithms. This is where Big O notation comes into play. Big O notation provides a standardized way to express the worst-case time complexity of an algorithm or the scalability of a data structure. By analyzing and comparing the Big O complexities of popular DSA, we gain insights into their efficiency, allowing us to make informed decisions when selecting the most suitable approach for solving a problem. In this context, let's explore the Big O complexities of various commonly used data structures and algorithms in DSA, and understand their implications for performance and scalability. Let's discuss the Big O notation of some popular data structures and algorithms commonly used in DSA. Data structures and algorithms. Arrays. Accessing an element by index. O(1). Searching for an element. Linear search. O(n). Inserting an element at the end. O(1). Inserting an element at a specific index. O(n). Deleting an element from the end. O(1). Deleting an element from a specific index. O(n). Linked lists. Accessing an element by index. O(n). Searching for an element. O(n). Inserting an element at the beginning. O(1). Inserting an element at the end. O(1). Inserting an element at a specific index. O(n). Deleting an element from the beginning. O(1). Deleting an element from the end. O(1). Deleting an element from a specific index. O(n). Binary search trees. BST. Searching for an element. Average case. O(log n). Searching for an element. Worst case. Unbalanced BST. O(n). Inserting an element. Average case. O(log n). Inserting an element. Worst case. Unbalanced BST. O(n). Deleting an element. Average case. O(log n). Deleting an element. Worst case. Unbalanced BST. O(n). Hash tables. Insertion. Average case. O(1). Insertion. Worst case. With many collisions. O(n). Accessing an element. O(1). Deletion. O(1). Sorting algorithms. Bubble sort. O(n squared). Selection sort. O(n squared). Insertion sort. O(n squared). Merge sort. O(n log n). Quick sort. O(n log n). Average case. O(n squared). Worst case. Heap sort. O(n log n). Radix sort. O(k)n). Where k is the number of digits in the largest element. Graph algorithms. Breadth first search. BFS. O(v plus a). Where v is the number of vertices and a is the number of edges. Depth first search. DFS. O(v plus a). Dijkstra's algorithm. O(v plus a). log V, with a min heap priority queue. Prim's algorithm, minimum spanning tree, O, V plus A, log V, with a min heap priority queue. Driscoll's algorithm, minimum spanning tree, O, A log A, with sorting. It's important to note that these complexities represent the worst case scenarios or average case scenarios. In some cases, the actual performance of an algorithm can vary based on factors like input data, implementation details, and hardware considerations. However, Big O notation provides a standardized way to compare and analyze the scalability and efficiency of algorithms and data structures. When analyzing the time complexity of an algorithm using Big O notation, we drop the constant factors to focus on the overall growth rate as the input size increases. This practice allows us to understand the fundamental efficiency of an algorithm without getting caught up in specific implementation details. Let's explore this concept further with an example. Consider the following code snippet that prints the elements of an array. Def print elements. For I in print I. The loop iterates through each element in the array and prints it. Assuming the array has n elements, we might be tempted to say that the time complexity of this code is O n, since there is one loop that iterates through n elements. However, dropping the constant factor, we can simplify the time complexity to O1. Here's why. The loop iterates n times, where n is the size of the array. But when we drop the constant factor, we essentially consider the worst case scenario where n is arbitrarily large. In this worst case scenario, the growth rate of the algorithm becomes constant because the loop always iterates a fixed number of times for any input size. Therefore, no matter how large n becomes, the number of iterations remains the same, resulting in a constant time complexity. Thus, we express the time complexity of this code snippet as O1, indicating constant time complexity. Dropping the constants helps us focus on the dominant term that determines the growth rate of an algorithm. It allows us to compare algorithms more effectively and identify their scalability as the input size increases. By disregarding the constant factors, we abstract away the specific details of the implementation and gain a more abstract understanding of an algorithm's efficiency. When calculating the time complexity of an algorithm using Big O notation, we drop the non-dominant terms to focus on the most significant factors that determine the growth rate of the algorithm as the input size increases. By disregarding these non-dominant terms, we obtain a simpler and clearer representation of the algorithm's efficiency. Let's explore this concept further with an example. Let's consider an example. Def complex function n for I in range n. Print I for j in range n. For k in range n. Print j k. For underscore in range 100. Print hello world. In this code snippet, we have three parts. The first loop runs n times, where n is the input size. The nested loops iterate n times each, resulting in n squared iterations. The third loop iterates 100 times, which is a constant factor. If we were to analyze the time complexity without dropping any terms, we would express it as n plus n squared plus 100. However, when we drop the non-dominant terms, the time complexity simplifies to n squared. Here's the explanation. The nested loops have a time complexity of n squared, as they contribute the dominant factor to the overall growth rate. The first loop has a time complexity of n, and the third loop has a constant time complexity of 1. When we analyze the growth rate as the input size increases, the n squared term becomes much more significant compared to the n constant terms. Dropping the non-dominant terms. O n plus n squared plus 100 simplifies to O n squared, as n squared is the most influential factor that determines the growth rate. By dropping the non-dominant terms, we emphasize the most influential factor and provide a concise representation of the algorithm's growth rate. Dropping non-dominant terms allows us to focus on the core aspect of the algorithm's efficiency, making it easier to compare with other algorithms and understand its scalability. It simplifies the time complexity analysis while retaining the essential information about the algorithm's growth rate. Understanding how to analyze and combine runtime complexities in the context of big O notation is crucial for evaluating the efficiency and scalability of algorithms when comparing algorithms or considering multiple instances of the same algorithm. It is important to grasp the difference between adding and multiplying the runtimes. Adding runtimes does not change the overall time complexity as constant factors are ignored. However, multiplying runtimes can have a significant impact on the time complexity, potentially resulting in a higher growth rate. By comprehending these distinctions, we can accurately assess the performance of algorithms and make informed decisions about their suitability for solving problems efficiently. To understand the difference between adding and multiplying the runtime complexities in the context of big O notation, let's compare the add and multiply scenarios using the example with two for loops. In the add scenario, def add example n for I in range n print I, for j in range n print j. The overall time complexity is O n, because we have two separate loops that iterate n times each. When we add the runtimes together, O n plus O n simplifies to O 2n. However, in big O notation, we ignore the constant factor, so the time complexity remains O n. In the multiply scenario, def multiply example n for I in range n for j in range n print I j. The overall time complexity is O n squared, because we have nested loops. The outer loop runs n times, and for each iteration, the inner loop runs n times. As a result, the total number of iterations is n asterisk n equals n squared. Therefore, the time complexity becomes quadratic. O n squared. To summarize, in the add scenario, the time complexity is O n, indicating a linear growth rate. In the multiply scenario, the time complexity is O n squared, indicating a quadratic growth rate. The key difference is that adding the runtimes results in the same time complexity as the individual loops, O n, while multiplying the runtimes increases the time complexity to a higher growth rate, O n squared. This showcases the impact of combining the runtimes using addition versus multiplication in terms of their effect on the overall time complexity. Amortized time refers to the concept of analyzing the average runtime of operations in a data structure, taking into account both the worst-case scenarios and the typical cases. One example where amortized time is commonly used is with array lists or dynamically resizing arrays. Array lists provide the benefits of arrays while offering flexibility in size. As the capacity of the list grows dynamically as elements are inserted. When the capacity of the underlying array is reached, the ArrayList class creates a new array with double the capacity and copies all the elements to the new array, while the worst-case insertion time for a single element is O n. as it involves creating a new array and copying elements. This scenario rarely occurs. In most cases, the insertion time is O1. To capture the overall efficiency of the insertion operations, amortized time considers the infrequent worst-case scenario, balancing it with the much more common O1 case. In the case of array lists, after inserting X elements, the capacity is doubled at array sizes 1, 2, 4, 8, 16, and so on. The sum of this doubling sequence is roughly 2x, indicating that X insertions take O2x time. By dividing this by the number of insertions, the amortized time for each insertion is O1, providing a more accurate average estimation of the runtime. Example. Let's consider an example of appending elements to a dynamic array, similar to an array list. To demonstrate amortized time complexity, class dynamic array, def __init __ self capacity equals 1, self size equals 0, self array equals none, def append self element if self size equals self capacity, self resize self array self size equals element self size plus equals 1, def resize self new underscore capacity equals self capacity asterisk 2, new underscore array equals none asterisk new underscore capacity for I in range self size new underscore array I equals self array I self array equals new underscore array self capacity equals new underscore capacity. In this code snippet, the dynamic array class represents a dynamic array that resizes itself when needed. The append method is used to add elements to the array. When the size reaches the capacity, the resize method is called to double the capacity of the array. Let's analyze the amortized time complexity of the append method. Assuming the array starts with a capacity of 1, we will append n elements to the array. For the first element, the append operation takes O1 time since no resizing is needed. When the size reaches the capacity of 1, the next append operation triggers a resize. During the resize operation, the existing elements are copied to a new array with double the capacity. This copying process takes O(n) time. However, we need to consider that the resize operation occurs infrequently. Specifically, the resize operation occurs when the size of the array is a power of 2, i.e., 2, 4, 8, 16, etc. Let's assume that during the n append operations, the resize operation happens k times. Since the capacity is doubled each time, the total cost of the resize operations is roughly proportional to 1 plus 2 plus 4 plus 8 plus k. This is a geometric series, and the sum of such a series is approximately 2k. Therefore, the total cost of the resize operations is O2k. Since we are performing n append operations, the amortized time complexity for each append operation is O2k plus n. N approximately equals O2k n. This simplifies to O1, indicating that the amortized time complexity for each append operation is constant. In summary, even though resizing the array can be an expensive operation, it occurs infrequently and is amortized across multiple append operations. As a result, the average time complexity per append operation is constant. O1, providing efficient performance for a dynamic array data structure. Logarithmic time complexity, denoted as O log n, is a type of time complexity where the execution time of an algorithm increases logarithmically with the size of the input. This complexity typically arises when the algorithm reduces the problem size by a constant fraction with each iteration or recursion. To understand logarithmic time complexity, let's consider an example algorithm that performs binary search on a sorted array. Def binary underscore search. Target. Low equals 0. High equals len. 1. While low less than equals high. Mid equals low plus high. 2. If mid equals target, return mid. Elf mid less than target, low equals mid plus 1. Else high equals mid 1, return -1. In this code, the binary search algorithm repeatedly divides the search space in half, based on a comparison with the target element. It starts by comparing the target with the middle element of the array. If they match, the algorithm returns the index. If the target is greater, the algorithm narrows down the search space to the right half of the array. If the target is smaller, it narrows down the search space to the left half of the array. This process continues until the target is found or the search space is exhausted. The key insight here is that with each iteration of the while loop, the size of the search space is reduced by half. As a result, the algorithm quickly converges to the target element, significantly reducing the number of comparisons required. The number of iterations required to find the target element is determined by the logarithm base 2 of the size of the input array. This is because each iteration divides the search space in half, and the logarithm represents the number of times we can divide the input size by 2 until we reach 1. For example, if the input array has 8 elements, the binary search algorithm can find the target in at most log 2. 8 equals 3 iterations. Similarly, for an array of size 16, it takes at most log 2. 16 equals 4 iterations. As the input size grows, the number of iterations grows logarithmically. Hence, the time complexity of the binary search algorithm, and any other algorithm that exhibits a similar pattern of reducing the problem size by a constant fraction with each iteration, is O log n. It represents an efficient algorithmic complexity where the execution time increases slowly as the input size grows. Recursive algorithms play a fundamental role in computer science, offering elegant solutions to a wide range of problems. Understanding the time complexity of recursive algorithms is crucial for analyzing their efficiency and scalability. Recursive runtimes involve expressing the time complexity using recurrence relations, which describe how the runtime of a problem relates to the runtimes of its smaller subproblems. By solving these recurrence relations, we can determine the big O complexity of a recursive algorithm, providing insights into its performance characteristics as the input size grows. Recursive runtimes allow us to assess the efficiency of recursive algorithms and make informed decisions about their applicability and optimization. In this context, we will explore how to analyze the time complexity of recursive algorithms and derive meaningful insights about their computational efficiency. When analyzing the time complexity of recursive algorithms, we consider how the runtime grows as the input size increases. The runtime of a recursive algorithm is often expressed using recurrence relations, which describe the runtime of a problem in terms of smaller subproblems to calculate the big O complexity of a recursive algorithm. We typically solve the recurrence relation and determine its asymptotic behavior. Let's explore this concept further with an example. Consider the following recursive algorithm to compute the factorial of a number. Def factorial n. If n equals 0, return 1. Else, return n factorial n1. In this recursive function, We define the base case when n is 0, which returns 1. Otherwise, we recursively call the function with n1 and multiply it by n. To analyze the time complexity of this recursive algorithm, let's express it using a recurrence relation. Let's denote the runtime of factorial n as t n. The recurrence relation for this algorithm can be written as t n equals t n1 plus o 1. This equation states that the runtime of factorial n is equal to the runtime of factorial n1 plus some constant time operations o 1. To solve this recurrence relation, we can use a technique called recursion tree or unwinding the recursion. By visualizing the recursive calls as a tree, we can observe a pattern and derive the overall runtime. In the case of the factorial function, the recursion tree would have n levels, with each level representing one recursive call. At each level, there is a constant amount of work being done. O1. Since there are n levels in the recursion tree, the overall runtime can be approximated as O(n), as each level contributes O(1) work. Therefore, we can conclude that the time complexity of the factorial function implemented recursively is O(n), where n is the input size. It's important to note that the actual runtime may vary based on the specific implementation n. The underlying system's characteristics. However, when analyzing the complexity of recursive algorithms, we focus on the asymptotic behavior and the growth rate of the algorithm's runtime as the input size increases. Yes, it is possible to estimate the complexity of code programmatically. While it may not always provide an exact analysis, it can give you a good estimation of the complexity based on the code structure and input size. Here are a few approaches to consider. Counting operations. Analyze the code and count the number of operations or iterations that depend on the input size. For example, if there is a loop that iterates n times or a recursive function that is called k times, you can use these counts to estimate the complexity. Instrumentation. Add counters or timers to the code to measure the number of times specific operations are executed, or the overall runtime, by running the code with different input sizes and collecting these measurements. You can analyze the data and infer the complexity. Profiling tools. Use profiling tools that can automatically analyze the code and provide insights into its performance characteristics. These tools can track function calls, execution times, and memory usage, which can be used to determine the complexity of the code. Empirical analysis. Run the code with various input sizes and measure the execution times. Plot the data points and look for patterns or trends. Based on the growth rate of the execution times, you can estimate the complexity. Static code analysis. Utilize static code analysis tools that can analyze the code structure and provide complexity estimates. These tools can identify loops, recursive calls, and other patterns that contribute to the complexity. They can also suggest the big O notation or provide a range of possible complexities. It's important to note that programmatic complexity analysis may not always be precise, especially for complex algorithms or when there are multiple factors affecting the runtime. Theoretical analysis or mathematical proofs often provide more accurate complexity analysis. However, programmatic approaches can be helpful for quick estimations or when a theoretical analysis is not feasible. 1. Sum and product. Def calculate _sum and _product. N. Sum result equals 0. Product result equals 1. For I in range 1, n plus 1. First loop for calculating sum. Sum result plus equals I. for j in range 1, n plus 1. Second loop for calculating product. Product underscore result asterisk equals j. Print sum, quote, sum underscore result. Print product, quote, product underscore result. In this code, the first loop iterates from 1 to n and accumulates the sum of the numbers in the sum underscore result variable. The complexity of this loop is O n, since it performs a constant amount of work for each iteration. The second loop also iterates from 1 to n and multiplies the numbers together to calculate the product. Similarly, the complexity of this loop is O n, since the loops are sequential and not nested. The overall complexity of the code is the sum of the complexities of the individual loops, which is O n plus O n equals O 2n. However, we drop the constants while analyzing complexity, so the final complexity is O n. Therefore, the code with two sequential for loops, one for calculating the sum and the other for calculating the product, has a time complexity of O n, where n is the input size. 2. Array pairs. Def print underscore array underscore pairs. N equals len. For I in range n. Outer loop. For j in range I plus 1 n. Inner loop. Print I j. In this code, the outer loop iterates from 0 to n1, and the inner loop iterates from I plus 1 to n1, where I is the current value of the outer loop. This ensures that each pair of elements is printed only once, avoiding repetitions and unnecessary computations. The complexity of the outer loop is O n, since it runs n times. The complexity of the inner loop depends on the value of I and is approximately O n 2 on average. However, when analyzing complexity, we drop the non-dominant terms and constants, so we consider the inner loop to have a complexity of O n. Since the loops are nested, the total complexity is the product of the complexities of the individual loops, which is O n asterisk O n equals O n squared. Therefore, the code with two nested for loops, printing the elements of an input array in pairs, has a time complexity of O n squared, where n is the size of the input array. 3. Unordered pairs. Def print underscore array underscore unordered underscore pairs. N equals len. For I in range n. Outer loop. For j in range I plus 1 n. Inner loop. Print I j. In this code, the outer loop iterates from 0 to n1, and the inner loop iterates from I plus 1 to n1, where I is the current value of the outer loop. This ensures that each pair of elements is printed only once, avoiding repetitions. The complexity of the outer loop is O n, since it runs n times. The complexity of the inner loop depends on the value of I and can be approximated as O n 2 on average. However, when analyzing complexity, we drop the non-dominant terms and constants, so we consider the inner loop to have a complexity of O n. Since the loops are nested, the total complexity is the product of the complexities of the individual loops, which is O n asterisk O n equals O n squared. Therefore, the code with two nested for loops, printing the elements of an input array in unordered pairs, has a time complexity of O n squared, where n is the size of the input array. 4. Two array pairs. Def print underscore array underscore pairs. R1, R2, N1 equals len. R1, N2 equals len. R2. For I in range N1, hash outer loop for the first array. For j in range n2, hash inner loop for the second array. Print r1, I, r2, j. In this code, the outer loop iterates through the elements of the first array, and the inner loop iterates through the elements of the second array. This combination allows you to print all possible unordered pairs of elements from the two arrays. The complexity of the outer loop is O n1, where n1 is the size of the first array, as it runs n1 times. The complexity of the inner loop is O n2, where n2 is the size of the second array, as it runs n2 times. Since the loops are nested, the total complexity is the product of the complexities of the individual loops, which is O n1 asterisk O n2 equals O n1 asterisk n2. Therefore, the code with two nested for loops, printing the elements of two input arrays in unordered pairs, has a time complexity of O n1 asterisk n2, where n1 is the size of the first array and n2 is the size of the second array. 5. Reverse array. Def reverse underscore array. N equals len. Start equals 0. End equals n1. While start less than end. Hash swap elements at start and end indices. Start. End. Equals end. Start. Hash move the start and end indices towards the center. Start plus equals 1. End equals 1. Return In this code, we have a while loop that continues until the start index becomes greater than or equal to the end index. Within the loop, we swap the elements at the start and end indices using tuple unpacking. Then, we increment the start index and decrement the end index to move towards the center of the array. The time complexity of this code is O n2, which simplifies to O n, where n is the size of the array. Since the loop runs until the midpoint of the array, the number of iterations is proportional to the size of the array. Therefore, the code with a loop to reverse an array has a time complexity of O n, where n is the size of the array. 6. Find equal complexity. Explain which of these below complexities are equal. O n plus k, where k less than n. O 2n. O n plus log n. O n plus m. Let's analyze each complexity expression. O n plus k, where k less than n. In this case, we have two variables, n and k. Since k is less than n, it can be considered as a constant factor. Therefore, O n plus k simplifies to O n. The complexity is linear with respect to the input size n. O 2n. The expression O 2n can be simplified by dropping the constant factor, which results in O n. It represents linear complexity, similar to the previous case. O n plus log n. In this expression, we have two terms, n and log n. The logarithmic term typically grows slower than the linear term as n increases. However, when analyzing complexity, we consider the most dominant term. In this case, the linear term dominates, and the logarithmic term can be dropped. Hence, O n plus log n simplifies to O n. O n plus m. In this expression, we have two variables, n and m. The complexity notation O n plus m represents that the algorithm's time complexity is dependent on both n and m, without specifying any relationship between them. It is not possible to simplify this expression further unless additional information about the relationship between n and m is provided. To summarize, the complexities O n plus k, O 2n, and O n plus log n are all equivalent and represent linear time complexity. denoted as O, n. The complexity O, n plus m, represents a dependency on both n and m without specifying their relationship. 8. Prime number. Import math. Def is _prime _recursive. N. Divisor equals 2. Hash base cases. If n less than 2. Return false. If divisor greater than math. ISQRT. N. Return true. If n% divisor equals 0. Return false. Hash recursive case. Return is _prime _recursive. N. Divisor plus 1. In this code, the is _prime _recursive function takes an input number n and a divisor, which starts from 2. The function uses recursion to check if n is a prime number by dividing it by integers from 2 to the square root of n. The code follows these steps. The base cases check if n is less than 2, not a prime number, if the divisor exceeds the square root of n, indicating that no factors have been found, and if n is divisible evenly by the current divisor. In the latter case, it means that n is not prime. If none of the base cases are met, the function makes a recursive call to itself, incrementing the divisor by 1. The complexity analysis of this algorithm can be broken down as follows. The loop performs SQRT n iterations, where SQRT represents the square root function. This is because if a number n has a factor greater than its square root, it must also have a corresponding factor smaller than its square root. Therefore, checking up to the square root is sufficient. In each iteration, the algorithm performs a constant amount of work, such as checking if n is divisible by the current divisor. Thus, the time complexity of the algorithm is O. SQRT n. The space complexity of the algorithm is determined by the maximum depth of the recursive call stack, which is also proportional to SQRT n. This means that the space complexity is also O. SQRT n. Overall, the code provides a recursive implementation to check if a number is prime by checking if it has any factors between 2 and its square root. The time complexity is O. SQRT n, where n is the input number, indicating an efficient approach for prime number checking. 9. Factorial. Def factorial n hash base case 0 equals 1. If n equals 0, return 1. Hash recursive case n equals n asterisk n1. Else, return n factorial n1. In this code, the factorial function takes an input number n and calculates its factorial recursively. The factorial of a non-negative integer n is defined as the product of all positive integers less than or equal to n. The code follows these steps. The base case checks if n is 0. In this case, the factorial is defined as 1. So the function returns 1. In the recursive case, the function calculates the factorial of n by multiplying n with the factorial of n1. Now let's analyze the complexity of this code. The number of recursive calls is equal to the input number n. In each recursive call, the function multiplies n by the factorial of n1. Therefore, the number of recursive calls is proportional to n, resulting in a time complexity of O. n. Additionally, the space complexity of this code is also O. n. Since it requires storing the recursive call stack, it's important to note that the recursive approach for calculating factorial is straightforward and easy to understand. However, for large values of n, it may lead to stack overflow due to the recursive calls. In such cases, an iterative approach or memoization technique can be used to avoid excessive recursion. Overall, the code provides a recursive implementation to calculate the factorial of a number. The time complexity is O(n), where n is the input number, indicating a linear relationship between the input size and the number of operations required. 10. Count all permutations. Def count _ permutations. String. Base case. If the string has only one character, there is only one permutation. If len string equals 1, return 1. Count equals 0. For I in range, len string fix the first character and recursively count permutations of the remaining characters. Count plus equals count _ permutations. String I plus string I plus 1. Return count. In this code, the count _ permutations function takes a string as input and counts all the possible permutations of that string using recursion. The code follows these steps. The base case checks if the length of the string is 1. In this case, there is only one permutation, the string itself, so the function returns 1. In the recursive case, the function iterates over each character of the string using a for loop. It fixes each character as the first character and recursively counts the permutations of remaining characters by making a recursive call to count _ permutations. The count of permutations is updated by adding the number of permutations obtained from recursive calls. Finally, the function returns the count of permutations. Now let's analyze the complexity of this code. The number of recursive calls is equal to the number of characters in the input string, which is n. In each recursive call, the function iterates over the remaining characters of the string, resulting in n iterations. Therefore, the number of recursive calls and iterations is proportional to n, resulting in a time complexity of O(n). The space complexity of this code is determined by the maximum depth of the recursive call stack, which is also proportional to n. It's important to note that calculating all permutations of a string is an inherently expensive operation, especially as the length of the string increases. The number of permutations grows factorially with the length of the string, resulting in an exponential increase in the number of recursive calls and iterations. Overall, the code provides a recursive implementation to count all permutations of a string. The time complexity is O(n), where n is the length of the string, indicating an exponential relationship between the input size and the number of operations required. 11. North Fibonacci No. Def Fibonacci _ recursive n base cases. Fib O equals 0. Fib 1 equals 1. If n equals 0, return 0. Elif n equals 1. Return 1. Recursive case. Fib n equals fib n1 plus fib n2. Else, return Fibonacci _ recursive n1 plus Fibonacci _ recursive n2. In this code, the Fibonacci _ recursive function takes an input number n and calculates the north Fibonacci number. Using recursion, the code follows these steps. The base cases check if n is 0 or 1. In these cases, the function returns the respective Fibonacci numbers. In the recursive case, the function calculates the north Fibonacci number by recursively calling Fibonacci _ recursive with n1 and n2, and adding the results together. Now let's analyze the complexity of this code. The number of recursive calls grows exponentially with the value of n. Each recursive call results in 2 additional recursive calls. Therefore, the number of recursive calls follows the Fibonacci sequence itself, resulting in a time complexity of approximately O(2)n. This exponential time complexity makes the recursive approach inefficient for calculating large Fibonacci numbers. The space complexity of this code is determined by the maximum depth of the recursive call stack, which is proportional to n. It's important to note that the recursive approach without dynamic programming suffers from redundant calculations, as the same Fibonacci numbers are computed multiple times. This leads to exponential time complexity and inefficient performance for larger values of n. To improve the efficiency, dynamic programming techniques such as memoization or tabulation can be used to avoid redundant calculations and reduce the time complexity to linear or O(n). Overall, the code provides a recursive implementation to find the nth Fibonacci number. The time complexity is exponential. O(2)n, where n is the input number, indicating an inefficient approach for large values of n. 12. Nth Fibonacci No. Using memoization. Def Fibonacci _ memoization. N. Memo equals. #check if the Fibonacci number is already calculated and stored in the memo. If n in memo, return memo. N. #base cases. Fib. 0 equals 0. Fib. 1 equals 1. If n equals 0. Result equals 0. Elif n equals 1. Result equals 1. Else. #recursive case. Fib. N equals fib. n1 plus fib. n2. Result equals Fibonacci _ memoization. n-1. Memo. Plus Fibonacci _ memoization. n-2. Memo. #store the calculated Fibonacci number in the memo. Memo. N equals result. Return result. In this code, the Fibonacci _ memoization function takes an input number n and uses memoization to calculate the nth Fibonacci number. The code follows these steps. The function checks if the Fibonacci number for n is already calculated and stored in the memo dictionary. If it exists, the function returns the stored value. The base cases handle the scenarios where n is 0 or 1, returning the respective Fibonacci numbers. In the recursive case, the function recursively calls Fibonacci _ memoization for n1 and n2 and adds the results together. The calculated Fibonacci number is stored in the memo dictionary to avoid redundant calculations. Finally, the result is returned. Now let's analyze the complexity of this code. The memoization technique eliminates redundant calculations by storing the Fibonacci numbers in the memo dictionary. The number of unique Fibonacci numbers that need to be calculated is equal to n. Each Fibonacci number is calculated once and stored in the memo. Therefore, the time complexity is O(n). As we only need to calculate the Fibonacci numbers once and retrieve the stored values for subsequent calls, the space complexity is also O(n). Since the memo dictionary stores the calculated Fibonacci numbers, by using memoization, we significantly reduce the number of computations required to find the Fibonacci number. The time complexity is improved from exponential to linear, resulting in efficient performance even for larger values of n. Overall, the code provides an optimized implementation to find the nth Fibonacci number using memoization. The time complexity is O(n), where n is the input number, indicating a much more efficient approach compared to the recursive approach without memoization. 13. Powers of 2. Here's an example of code to print the powers of 2 from 1 until the power of 2 is less than or equal to n. Def print _powers of _2. N. Power equals 1, while power less than equals n. Print power * equals 2. In this code, the print _powers of _2 function takes an input number n and prints the powers of 2 until the power of 2 is less than or equal to n. The code follows these steps. The function initializes the variable power to 1, representing the initial power of 2. It enters a while loop that continues until the value of power exceeds n. In each iteration, the current value of power is printed, representing the current power of 2. The value of power is then multiplied by 2 to calculate the next power of 2. Now let's analyze the complexity of this code. The code uses a while loop that continues until the value of power exceeds n. The number of iterations depends on the value of n. In each iteration, the code performs constant time operations, printing the current power and updating the value of power by multiplying it by 2. The number of iterations in the while loop is determined by the logarithm base 2 of n, which can be represented as log 2 n. Therefore, the time complexity of this code is O log n, as the number of iterations is logarithmic with respect to the input size. The space complexity is constant, as the code only requires a few variables to store intermediate values. The code provides an efficient approach to print the powers of 2 until the power of 2 is less than or equal to n. The time complexity is logarithmic. O log n, indicating a logarithmic relationship between the input size and the number of operations performed. It efficiently prints the desired output without requiring excessive iterations or complex calculations. 14. Breadth first search. BFS. Perform a breadth first traversal of a graph starting from a given source vertex. From collections import dec. Def BFS. Graph. Source. Visited equals set. Q equals dec. Source. Visited dot add. Source. While Q. Vertex equals Q. Pop left. Print. Vertex. End equals. For neighbor in graph. Vertex. If neighbor not in visited. Q. Append. Neighbor. Visited dot add. Neighbor. Complexity analysis. Time complexity. O. V plus A, where V is the number of vertices and A is the number of edges in the graph. Explanation. BFS visits each vertex and edge once. The time complexity is determined by the number of vertices and edges in the graph. 15. Dijkstra's algorithm. Find the shortest path between two vertices in a weighted graph. Import heap Q. Def Dijkstra. Graph. Source. Distances equals vertex. Float. INF. For vertex in graph. Distances. Source. Equals 0. PQ equals O. Source. While PQ. Dist. Vertex equals heap Q. Heap pop. PQ. If dist greater than distances. Vertex. Continue. For neighbor. Weight in graph. Vertex. Items. New underscore dist equals dist plus weight. If new underscore dist less than distances. Neighbor. Distances. Neighbor. Equals new underscore dist. Heap Q. Heap push. PQ. New underscore dist. Neighbor. Return distances. Complexity analysis. Time complexity. O. V plus A. Log V. Where V is the number of vertices and A is the number of edges in the graph. Explanation. Dijkstra's algorithm finds the shortest path from a source vertex to all other vertices in a weighted graph. It uses a priority queue, min heap, to keep track of the vertices with the minimum distance from the source vertex. The algorithm proceeds as follows. Initialize the distance to the source vertex as 0 and all other vertices as infinity. Add the source vertex to the priority queue with a distance of 0. While the priority queue is not empty, do the following. Extract the vertex with the minimum distance from the priority queue. Relax all its neighboring vertices by updating their distances if a shorter path is found. Add the updated vertices to the priority queue. Continue until all vertices have been processed or the destination vertex is reached. The time complexity of Dijkstra's algorithm depends on the number of vertices v and edges a in the graph. In each iteration, the algorithm extracts the vertex with the minimum distance from the priority queue, which takes O log v time. For each vertex, the algorithm relaxes its neighboring vertices, which takes O1 time per edge. Therefore, the total time complexity is dominated by the operations on the priority queue, resulting in O v plus a log v. Note that if the graph is dense, a tilde v squared, the complexity can be approximated as O v squared log v. Optimizations using a binary heap or Fibonacci heap for the priority queue can reduce the time complexity to O v plus a log v or O v log v plus a, respectively, if the graph has non-negative edge weights. Using an optimized version like Dijkstra's algorithm with a heap, also known as Dijkstra's algorithm with a min heap, can further improve the time complexity to O v plus a log v. Space complexity. The space complexity of Dijkstra's algorithm is O v, as it requires a distance array to store the shortest distances from the source vertex to all other vertices. Additionally, the priority queue requires O v space. Overall, the algorithm has a space complexity of O v. In summary, Dijkstra's algorithm efficiently finds the shortest path in a weighted graph by utilizing a priority queue. Its time complexity depends on the number of vertices and edges in the graph, while its space complexity is proportional to the number of vertices. Welcome to the practice exercises on complexity. Understanding and analyzing the complexity of algorithms is a vital skill in computer science and software development. These exercises are designed to enhance your understanding of complexity analysis and provide you with hands-on experience in evaluating the efficiency of different algorithms. You will explore concepts such as big O notation, best case, worst case, and expected case analysis, dropping constants and non-dominant terms, amortized time, and more. Each exercise presents a problem or scenario along with coding examples that allow you to analyze the time and space complexity of the solution. By actively engaging in these practice exercises, you will sharpen your algorithmic thinking and gain proficiency in assessing the efficiency of algorithms. So, let's dive in and master the art of complexity analysis. Problems. 1. Product of A and B without operator. Int product. Int A. Int B. Opening curly bracket. Int sum equals 0. For int I equals 0. I less than B. I plus plus. Opening curly bracket. Sum plus equals A. Closing curly bracket. Return sum. Closing curly bracket. 2. Modulus. A percent B. Without using the modulo operator. Percent. Def modulus. A. B. While A greater than equals B. A equals B. Return A. 3. Division. A. B. Without using the divide operator. Slash. Def division. A. B. If B equals 0. Raise 0 division error. Division by 0 is undefined. Quotient equals 0. Sign equals -1 if A less than 0. Caret. B less than 0. Else 1. A equals ABS. A. B equals ABS. B. While A greater than equals B. A equals B. Quotient plus equals 1. Return sign quotient. 4. Square root. To compute the integer square root of a number, we can use a guessing approach by starting with an initial guess and iteratively refining it until we find the closest integer square root. Here's an example of code that implements this approach. Def integer underscore square underscore root n. If n less than 0, return -1. If n equals 0, return 0. Guess equals n, 2. While true, difference equals guess asterisk guess, n. If difference equals 0, return guess. Elif difference less than 0. Low equals guess. Guess equals guess plus n. 2. If low equals guess, return -1. Else, high equals guess. Guess equals guess plus 0. 2. If high equals guess, return -1. 5. Element in advanced BST. How long it takes, worst case, to find an element in an unbalanced binary search tree. 6. Append to new. The append to new function adds a value to an array by creating a new array with a larger size n. Returning this extended array. You have utilized the append to new function to develop a copy array function, which repeatedly invokes append to new. What is the time it takes to copy an array? Here's an example code that demonstrates the append to new method and uses it to create a copy array function. Def append to new value hash create a new array with increased length. New equals none asterisk len plus 1 hash copy elements from the original array to the new array. For I in range len new I equals I hash append the new value to the end of the new array. New len equals value hash return the new array. Return new def copy array hash create an empty array. Copy equals hash iterate over the elements in the original array. For I in range len hash append each element to the new array using append to new method. Copy equals append to new. Copy I hash return the copied array. Return copy hash example usage. Original array equals 1, 2, 3, 4, 5. Copied array equals copy array. Original array. Print. Original array. Quote. Original array. Print. Copied array. Quote. Copied array. 7. Sum of digits. Def sum digits. Num. Hash convert the number to a string. Num str equals str. Num. Hash initialize the sum. Digitsum equals 0. Hash iterate over each character in the string. For char in num str. Hash convert the character back to an integer and add it to the sum. Digitsum plus equals int. Char. Hash return the sum of digits. Return digitsum. Hash example usage. Number equals 12,345. Result equals sum digits. Number. Print. Sum of digits. Quote. Result. 8. Print all strings. Here's an example code that prints all strings of length k where the characters are in sorted order. Def print sorted strings. K. Set equals A, B, C. Hash example character set. String equals single quote asterisk k hash initialize an empty string of length k. Print sorted strings helper. K. String. Set. 0. Def print sorted strings helper. K. String. Set. Index. Hash base case. If index is equal to k, we have generated a valid string. If index equals k, print. Join. String. Else. Hash try each character from the character set at the current index. For I in range len set. String. Index. Equals set. I. Print sorted strings helper. K. String. Set. Index plus 1. Hash example usage. K equals 3. Print sorted strings. K. 9. Intersection of two arrays using binary search. Def intersection A, B, hash sort array B, B, sort, hash initialize the intersection count. Intersection count equals 0. Hash iterate through array A. For num in A, if binary search B, num, intersection count plus equals 1. Return intersection count. Def binary search target, low equals 0, high equals len, 1, while low less than equals high. Mid equals low plus high, 2. If mid equals target, return true. Elf mid less than target, low equals mid plus 1. Else high equals mid 1, return false. Hash example usage. Array A equals 1, 3, 5, 7, 9. Array B equals 2, 4, 6, 8, 10. Result equals intersection. Array A, array B. Print intersection count. Quote. Result 10. Maximum subarray sum. Given an array of integers, find the contiguous subarray with the largest sum. Def max subarray sum. Max sum equals float. INF. Cursum equals 0. For num in R, cursum equals max. Cursum plus num. Num. Max sum equals max. Max sum. Cursum. Return max sum. 11. Depth first search. DFS. On a graph, perform a depth-first traversal of a graph starting from a given source vertex. Def DFS. Graph. Source. Visited. Visited.add. Source. Print. Source. End equals. For neighbor in graph. Source. If neighbor not in visited. DFS. Graph. Neighbor. Visited. 12. Longest increasing subsequence. Find the length of the longest increasing subsequence in an array. Def longest increasing subsequence. Nums. N equals len. Nums. dp equals 1. Asterisk n. For I in range. 1. N. For j in range. I. If nums. I. Greater than nums. J. dp. I. Equals max. dp. I. dp. j. Plus 1. Return max. dp. 13. N-queens problem. The n-queens problem involves placing n-queens on an n times n chessboard such that no two queens threaten each other. Here's the code for it. Def solve _n_ queens. N. Def backtrack. Row. Queens. If row equals n. Result. Append. Queens. Return. For call in range. N. If all. Row. I. Equals abs. Call. Queens. I. For I. Row in enumerate. Queens. Row. Backtrack. Row plus 1. Queens plus. Call. Result equals. Backtrack. O. Return result. 14. Permutations problem. Given a collection of distinct integers. Return all possible permutations. Here's the code for it. Def permute. Nums. Def backtrack. Start. If start equals len. Nums. Result. Append. Nums. For I in range. Start. Len. Nums. Nums. Start. Nums. I. Equals nums. I. Nums. Start. Backtrack. Start plus 1. Nums. Start. Nums. I. Equals nums. I. Nums. Start. Result equals. Backtrack. O. Return result. 15. Combination sum problem. Given a set of candidate numbers and a target sum. Find all unique combinations where the candidate numbers sum to the target. Here's the code for it. Def combination _ sum. Candidates. Target. Def backtrack. Start. Cur _ sum. Combination. If cur_sum equals target. Result. Append. Combination. Return. If cur_sum greater than target. Return. For I in range. Start. Len. Candidates. Combination. Append. Candidates. I. Backtrack. I. Cur_sum plus candidates. I. Combination. Combination.pop. Result equals. Candidates. Sort. Backtrack. 0. O. Return result. Solutions. 1. Product of A and B without operator. The given code calculates the product of two integers, A and B, using a loop. The time complexity of this code can be analyzed as follows. The loop iterates B times. As the loop condition is I less than B. Within each iteration, a constant time operation is performed, which is the addition of A to the variable sum. Therefore, the time complexity of the code is O. B, as the number of iterations is directly proportional to the value of B. The space complexity of the code is constant, as it only uses a few variables, A, B, sum, and I, regardless of the input size. In summary, the given code has a time complexity of O. B, where B represents the second input parameter. This indicates that the runtime of the code will increase linearly with the value of B. 2. Modulus. %B. Without using the modulo operator. The number of iterations in the while loop depends on the quotient of A divided by B. In the worst case scenario, when A is much larger than B, the number of iterations will be approximately A, B. Therefore, the time complexity of this code can be represented as O. A, B, or more generally as O. Max. A, B, min. A, B. The space complexity of the code is constant, as it only uses a few variables, A, B, and the loop counter. It's important to note that the time complexity of this code can vary significantly depending on the values of A and B. In some cases, the code may run in constant time. O. 1. If A is much smaller than B. However, in the worst case scenario where A is much larger than B, the time complexity can approach O. A. 3. Division. A, B. Without using the divide operator. The number of iterations in the while loop depends on the quotient of A divided by B. In the worst case scenario, when A is much larger than B, the number of iterations will be approximately A, B. Therefore, the time complexity of this code can be represented as O. A, B, or more generally as O. Max. A, B, min. A, B. The space complexity of the code is constant, as it only uses a few variables, A, B, quotient, and sign, regardless of the input size. It's important to note that the time complexity of this code can vary significantly depending on the values of A and B. In some cases, the code may run in constant time. O. 1. If A is much smaller than B. However, in the worst case scenario where A is much larger than B, the time complexity can approach O. A. 4. Square root. The while loop continues until the guess stops changing, which happens when the result is not a perfect square. The number of iterations depends on the closeness of the initial guess to the integer square root of n. In the worst case scenario, the number of iterations can be considered logarithmic to the input n. Therefore, the time complexity of this code can be represented as O log n. The space complexity of the code is constant, as it only uses a few variables, n, guess, difference, low, and high, regardless of the input size. It's important to note that the time complexity of this code may vary slightly depending on the magnitude of n. but it generally performs with logarithmic complexity, making it an efficient approach for finding integer square roots. 5. Element in advanced BST. If a binary search tree is not balanced, meaning its structure is skewed towards one side, it can significantly impact the time it takes to find an element. Particularly in the worst-case scenario. In a balanced binary search tree, the height of the tree is logarithmic to the number of nodes. This allows for efficient searching, as each comparison eliminates approximately half of the remaining nodes at each step. However, in an unbalanced binary search tree, the height of the tree can become equivalent to the number of nodes. This happens when the tree resembles a linked list, with all nodes aligned in a straight line. In this case, searching for an element would require traversing through every node, resulting in a linear search time. Here's an example of code that demonstrates the worst-case scenario for searching an element in an unbalanced binary search tree. Class node def__init__ self value equals value, self left equals none, self right equals none. Def insert root value. If root is none, return node value. Elif value less than root value. Root left equals insert root left value. Else root right equals insert root right value. Return root. Def search root value. If root is none or root value equals value, return root. Elif value less than root value. Return search root left value. Else return search root right value. Hash example usage. Root equals none. Root equals insert root. 5. Root equals insert root. 3. Root equals insert root. 7. Root equals insert root. 2. Root equals insert root. 4. Root equals insert root. 6. Root equals insert root. 8. Element _to_ find equals 8. Result equals search root. Element _to_ find. If result is not none, print element _to_ find found in the binary search tree. Else print element _to_ find not found in the binary search tree. In this code, we create a binary search tree with unbalanced nodes. The insert function is used to insert nodes into the tree, while the search function is used to find a specific value in the tree. The worst-case scenario occurs when the element being searched for is located at the deepest level of the unbalanced side of the tree. This would require traversing through all nodes, resulting in a time complexity of O(n), where n is the number of nodes in the tree. To improve the search time in an unbalanced binary search tree, it's essential to balance the tree by performing appropriate rotations or using self-balancing tree structures like AVL trees or red-black trees. These techniques ensure that the height of the tree remains logarithmic to the number of nodes, enabling efficient searching with a time complexity of O log n. 6. Append to new. In this code, the append to new method takes an array R and a value. It creates a new array new R with a length that is one element longer than the original array. Then, it iterates over the elements in the original array, copies them to the new array, and finally appends the value to the end of the new array. The append to new method returns the new array. The copy array function uses the append to new method to create a copy of the original array. It initializes an empty array copy R and then iterates over each element in the original array. For each element, it calls the append to new method to append it to the copy R. Finally, it returns the copied array. The time complexity of the append to new method is O n, where n is the length of the original array. This is because it needs to copy all the elements from the original array to the new array, which takes linear time. The time complexity of the copy array function is O n squared, where n is the length of the original array. This is because for each element in the original array, the append to new method is called, which has a time complexity of O n. Since append to new is called n times, the overall time complexity becomes O n, or O n squared. This is not an efficient approach for copying arrays, especially for large arrays, as it involves creating new arrays and copying elements repeatedly. 7. Sum of digits. In this code, the sum digits function takes a number num as input. It converts the number to a string and initializes a variable digitsum to store the sum of digits. Then, it iterates over each character in the string representation of the number. For each character, it converts it back to an integer using the int function and adds it to the digitsum. Finally, it returns the digitsum, which represents the sum of digits in the original number. The time complexity of this code is O log n, where n is the value of the input number. Since we convert the number to a string representation, the number of digits in the number determines the time complexity. The number of digits in a number n is proportional to log n, with base 10. Therefore, as the input number increases, the time complexity grows logarithmically. 8. Print all strings. In this code, the print sorted strings function takes an integer k as input. It initializes an empty string of length k and a character set k set, e.g., A, B, C. It then calls the print sorted strings helper function to generate all strings of length k where k characters are in sorted order. The print sorted strings helper function is a recursive helper function. It takes the length k, the current string, the character set k set, and an index indicating the current position in the string. It uses a backtracking approach to generate all possible strings. If the index is equal to k, it means a valid string has been generated. So it prints the string. Otherwise, it iterates over each character in the character set and assigns it to the current index of a string. Then, it recursively calls itself with the updated string and increments the index by 1. The time complexity of this code is O n caret k, where n is the size of the character set and k is the length of the string. Since we generate all possible strings of length k, the number of recursive calls is n caret k. Each recursive call takes constant time to print the string. So the overall time complexity is O n caret k. It's worth noting that the space complexity of this code is O k, as we use an additional string of length k to store the generated strings during the recursion. 9. Intersection of two arrays using binary search. In this code, the intersection function takes two arrays A and B as input. It sorts the array B using the sort method. Then, it initializes the intersection count to 0. Next, it iterates through each element in array A. For each element, it performs a binary search in array B using the binary search function to check if the element is present. If the element is found, it increments the intersection count. Finally, it returns the intersection count. The binary search function implements the binary search algorithm to search for a target value in a sorted array. It maintains two pointers, low and high, that represent the range of the search. It repeatedly calculates the middle index mid and compares the value at mid with the target. If the target is found, it returns true. If the target is less than the value at mid, it narrows the search range to the left half by updating high. If the target is greater than the value at mid, it narrows the search range to the right half by updating low. The function continues this process until the target is found or the search range is exhausted, returning false in the latter case. The time complexity of this code is O n log m, where n is the length of array R and m is the length of array B. Sorting array B takes O m log m time, and the binary search for each element in array A takes O n log m time. Therefore, the overall time complexity is dominated by the binary search process. 10. Maximum subarray sum. Complexity analysis. Time complexity. O n. Explanation. The algorithm iterates through the array once, maintaining the maximum subarray sum. The time complexity is linear because each element is processed only once. 11. Depth first search. DFS. On a graph. Complexity analysis. Time complexity. O v plus a, where v is the number of vertices and a is the number of edges in the graph. Explanation. DFS visits each vertex and edge once. The time complexity is determined by the number of vertices and edges in the graph. 12. Longest increasing subsequence. Complexity analysis. Time complexity. O n squared, where n is the length of the input sequence. Explanation. The longest increasing subsequence problem aims to find the length of the longest subsequence in a given sequence such that the elements are in increasing order. The list problem can be solved using dynamic programming. The algorithm proceeds as follows. Initialize an array dp of length n, where dp I represents the length of the longest increasing subsequence ending at index I. Set each dp I to 1 initially since the minimum length of any subsequence is 1. Iterate over the input sequence from left to right. For each index I, iterate over all previous indices j from 0 to I1. If the element at index I is greater than the element at index j, update dp I as max dp I dp j plus 1. After the iteration, the maximum value in the dp array represents the length of the longest increasing subsequence in the input sequence. The time complexity of the list algorithm is O n squared, because there are nested loops involved. The outer loop iterates over each element of the sequence, resulting in O n iterations. The inner loop iterates over all previous elements, resulting in O n iterations in the worst case. Therefore, the overall time complexity is O n squared. Optimizations. The time complexity of the list problem can be improved to O n log n, using more advanced algorithms like the patience sorting algorithm or binary search. These algorithms utilize data structures like binary search trees or segment trees to efficiently search and update the list information. Space complexity. The space complexity of the list algorithm is O n, because we need an array of size n to store the list lengths. In summary, the longest increasing subsequence problem can be efficiently solved using dynamic programming with a time complexity of O n squared. There are also more optimized algorithms available with a time complexity of O n log n. The space complexity is O n, since we only need an array to store the list lengths. 13. N-queens problem. The time complexity of the n-queens problem solution is O n, where n is the size of the chessboard. This is because, in the worst case, there can be n possible configurations to check. The space complexity is O n, as we need to store the position of each queen for each valid configuration. 14. Permutations problem. The time complexity of the permutations problem solution is O n, where n is the size of the input array. This is because there are n possible permutations to generate. The space complexity is O n, as we need to store the temporary permutations during backtracking. 15. Combination sum problem. The time complexity of the combination sum problem solution depends on the number of valid combinations. In the worst case, there can be 2 target per minute candidates combinations to check. The space complexity is O target per minute candidates, as we need to store the combinations during backtracking.